Well, thank you everyone for coming to my session, and I hope you've been enjoying GTC so far, as well as the keynote. This talk is to do a little bit of a double click on some of the infrastructure and hardware and ecosystem that Jensen talked about in the keynote. So I'm going to click through and explain, what it is that makes NVIDIA tick, and how do we take that technology and turn it into tokens to do some amazing stuff, mostly not by NVIDIA, but by everyone here at GTC and all the developers. So we'll get started. As Jensen likes to say, we're a 5-layer cake, from the energy to the chips to all the different platforms we build to the models and, of course, to the applications that make all that possible. It's through, in the very beginning, when we started CUDA, to think about not just building an instruction set for a new kind of processor or a programming model or a compiler, but to think about the applications from the very beginning. We did a roadshow, and we tried to understand, what do people want to do with GPUs? They'd heard about them. They'd heard they could do some things that were a little bit different than playing video games. And it always comes back to the workloads. People didn't want to necessarily learn new programming models or retrain everything. They wanted to understand how could they make their workloads faster. And since that first roadshow, and since CUDA is now 20 years, we launched it in 2006, we've been thinking about all of those workloads and the entire stack to make them run efficiently, fast, and every year, newer, better, and more interesting. And that has culminated in a massive number of libraries. And when we started, we had a very simple set of libraries. There was a library called cuBLOS, or Basic Linear Algebra Subroutines, known in the HPC world as matrix multiplies. And we had an FFT library for signal processing. Today, we have over 1,000 different SDKs and models. You now ship both. We have over 6,000 major accelerated applications out in the world, with over 600 million downloads of all these libraries and over 7 million developers. Some of the libraries are interesting. One of the best parts about my job is I get to learn about a whole new field of science, a whole new thing that we can accelerate. CUEST, or CU Electron Structure Theory Library, is specifically a library to actually simulate the wave nature of atoms and electrons. Simulating things all the way down those sort of quantum states allows material scientists to actually simulate or predict the material properties of new materials. How well they bend, their conductivity, their elastic behaviors, so they can actually design and study and predict new kinds of materials for airplane wings or turbine engines or toothbrushes. It's a fascinating area. It's actually used a lot in building some of these chips. TSMC and others are using CUEST to actually predict new kinds of semiconductor materials. The libraries that you see here is a small swath of the things that we do, but as you can see, they're all focused in different areas. Wherever NVIDIA can add a library to help a developer to accelerate an application, we do that. In some cases, those verticals need much more. They need a suite of libraries or a set of tools. So we'll open up a platform, Aerial, for example, for doing 5G radio, and many others you see here. And people do amazing stuff with our platform. It's really exciting to see it. One of them is up here. The DNA sequencing Guinness Book of World Records was just recently broken. This was work in collaboration with Roche, the Broad Institute, and Boston Children's Hospital. They used a toolkit called NVIDIA Parabricks, which is specifically used for DNA sequencing. They actually were able to sequence a DNA in just 4 hours. That's in comparison to the first human genome project, which took in 2003, which took 13 years and $3 billion. This was done in about 4 hours on a small cluster of GPUs in Google Cloud. Faster MRIs. MRIs were one of the first use cases of GPUs, taking the signals off of the raw magnet and converting it into a 3D image. Today, they now use AI. This is a company called Blue Seal Horizon. They built the first 3 Tesla MRI machine that does not use or waste any helium. I had no idea, but apparently when you get an MRI, you use about 2,000 liters of helium. Don't know where all that goes. But they've actually built a new kind of MRI machine, and they're using AI to make it work, and they make it work really fast. Using our Clara platform with our Monet libraries, it can actually take the MRI data, put it through an AI model, which quickly does segmentation and reconstruction of the 3D model so that it can, in real time, give you a preview of your scan or a 3D view of your brain or your organs, so you don't have to wait for that answer. You can just see it immediately at the operator's desk. Well, Jensen talked a little bit about the scaling laws, and for the rest of this talk, I'm going to talk about some of the ways that we make these scaling laws faster and how you can benefit. Certainly at the beginning is pre-training. This is where the AI model is a completely blank brain and simply is fed the contents of the internet and learns its basic knowledge. Some of the largest data centers in the world are used for pre-training to scale out to actually build those the starting point for those trillion parameter models. But that's insufficient. After they get pre-trained, you then have to go through post-train scaling. Post-train scaling takes that knowledge and makes it useful. It teaches the model how to think. And I'll give you a demo of that in a second. If you have a knowledge, it will echo back what it knows, but it can't actually do anything useful. It can't think, it can't code, it can't answer a question effectively. We actually use I often see as many GPUs used for post-training as they are for pre-training in order to become and get smarter. This is the model. It's learned its book smarts, is now going into school and actually figuring out how to apply that knowledge. After that, there's test time scaling. This is where we actually do problem solving. And I'll show you how these models need to actually think before they give the answer. Just 2 years ago, they used to just say what they knew. Now they actually take some time to actually work out a problem before telling you the answer. And then the new field of scaling, which is agentic scaling. This new feature, like OpenClaw, we have agents, talking to other agents. And in the past, AI was the performance of AI was how fast an AI could talk to you. And then you would give it a prompt and a response. Now we have an AI agent talking to another AI, and those two things can happen at the speed of those two AIs can think and talk back to each other. That's giving them an ungated performance and intelligence capability that's really ramping up the number of tokens and the compute capability. Also, here's an example of once you've done some basic pre-training, the model has some knowledge. This is a llama model. You ask it what is Nvidia, and it knew this from the internet. The common crawl, I think, is about 100 trillion tokens. This is the internet. So if you put the internet and put it into tokens, you get about 100 trillion. And you can train a model on that, and it'll spit out what it knows. Fairly accurate. But it can't really think. If you don't teach a model to think, it's just going to try to spit out what it knows. Maybe someone asked that question on the internet, and it gets it wrong. So if you give it a problem like, I need to figure out where to seat my family of 8 for dinner at a round table. My in-laws don't get along with my parents. My sister needs to sit next to her kids. My wife doesn't really want to sit next to my mom. And where should everyone be seated? I think we can relate to this question. And you give it to a basic model like the original llama models, and it will, that's a complex family dynamic. Don't worry, I'm here to help you. This challenging situation. Here's a suggestion. Step 1, separate tables. Consider separate table for your in-laws and parents. That way they won't have to interact with each other and you can still have a family gathering. That is literally what Llama 8B gave me when I gave it this prompt, which I thought was hilarious. So this is an example of it. Maybe it should think before it answers and try to, instead of just come up with I'm sure some wedding guide had this on their website. Let me show you what a model like DeepSeek does. So DeepSeek, which came out a little over a year ago, really showed the world what thinking is about. And this is a post-trained model that is not only post-trained of how to think, but actually before answering the question, it thinks internally, and then it outputs the output token to you. And it's a very different experience. If I give it the same question, it actually will go and think. And these are all the tokens that it's generating behind the scenes, trying to figure out this combinatorial problem. And sure enough, it totally gets it right. Seat your family of 8 harmonious around a table. You, wife, dad, mom, sister, little brother, mother-in-law, father-in-law, all the key conditions are met. in-laws and parents, sisters and brothers adjacent, mom, wife, not next to each other. Phew. Separated by you and dad, even helped you out there. If you actually, so DeepSeek is an open model, you can actually watch it and see what it's doing. And it's very clever. It runs through the combinatorial thing, and it comes up with an answer. And once it comes up with the first answer, it doesn't answer right away. It actually says, let me check my answer. And you can see in here, it actually checks its answer and says, yes, that's correct. And then it doesn't give you the answer then. It says, let me triple check, and runs it again and tries to confirm. That's very intentional. These are thinking models, and the DeepSeek engineers purposely train the model to figure it out by using all these tokens. These are tokens you're paying for, by the way, and come up with an answer and check twice. And that's how they got the accuracy that was so close to GPT at the time and blew the doors open. To do this, you have to have an intelligent model, more than just A/B, and you have to have it run fast. You can't sit around and wait for 3,000 tokens and sit there and twiddle your thumbs. You're waiting for that answer. So your time to first token really matters. Inference speed matters. And this is what makes models today super intelligent. Whether you're using talking to ChatGPT or using Claude Code, they need to think, they need to process, generate a lot of tokens, come up with an answer, and do it accurately. That pushes huge pressure on the model builders to build smarter models that still can run kind of fast, but have extensive knowledge. And that's kind of where this idea of mixture of experts came from. We can build smarter models just by making them bigger, add more neurons, more parameters, go from 8 billion to 30 to 100. But the problem is it gets exponentially hard to compute all of those parameters. These are neurons that are doing math along the way to go from the beginning to the end to give you that first token. And then every token, I got to go through all the math. Well, that's using every neuron in the brain to compute every answer. And that's not very efficient. Not every neuron, not every parameter, not every connection in the network is necessary. Mixture of experts is actually an optimization technique. What we do is we take these dense neurons and we just split them up into separate experts. And the experts, there's a router which is trained during the training process to know this expert is probably the person who can help answer this question, but maybe this one and this one and this one. Not all of them. And K2, which recently came out, has a huge number of experts, 384 separate experts, but it just picks 8 for every layer. So the 8 of you would then, the few of you that would have it, you would pick up the answer, and the next layer we talk to the next 8 of you, and so forth and so forth. So while this Kimi K2 is actually a trillion parameter model, it actually only uses about 32 billion parameters for every inference, making it more real time. Compared to Llama 33B, which uses all 33 billion parameters every time it generates a token. And you can see the intelligence difference. This, according to artificial analysis, this is an intelligence score of 14, and Kimi K2 is up to 47. So it's a big uplift, much larger model, much more efficient. Almost all thinking models today are a mixture of experts. The ones you're hearing about today, all of that is the most efficient way to generate code and to generate output and to be smart. But there's a hidden cost to all that, and that's where we're getting to with the hardware, is the amount of communication that has to happen. The way you lay out an expert across a rack is actually doing a wide expert parallel, basically putting each expert on every different GPU inside of that rack that Jensen showed on stage, and the experts are constantly having to talk to each other. Typically, you're not even answering, if I may be answering one question, but most of those racks and systems are actually serving multiple questions and queries at the same time. And we have a massive amount of communication that's happening between all of the GPUs, running all the experts, trying to generate this model very efficiently. This was the genesis for building the NVSwitch and the NVLink. In the middle of that rack, you have 9 separate NV switches, each with 2 switch chips that are specifically designed to actually do all of that communication as fast as possible. We don't want to be waiting on communication when we should be computing to generate these tokens. This is actually the first generation, the engineering original ES sample for our NV switch. You can see the sheer number of wires and connections that go out. This is just one of the 9 switches. There's 2 switches here and here, liquid cooled. And they actually would, the ones in the gold ones in the back would connect to the back of the rack, and the blue ones in the front would come out the front, so you can cable 2 racks together to scale up the number of GPUs. That's just one. You have 9 of them. It's a lot of cables, a lot of wires, a lot of switches. But that gave you the performance that we were seeing. In contrast, if you try to do it without, you could maybe do, we had before only 8 GPUs in a server. You'd have to put all 48 of those experts, 48 experts on each GPU. But because if you didn't have a switch, you'd have to split your communication. You'd only get like 260 gigabytes per link. If I tried to scale up and throw more GPUs to go faster, I now can put 6 experts per GPU, so that makes it a little bit faster. I've got a lot more expert competition happening in parallel, but my scale up is limited by Ethernet. And even with today's Ethernet, you're getting at max about 100 gigabytes per second per GPU. That's not a lot, and in fact, it's even slower than using an 8-way. If you go with NVLink, you're getting 72 GPUs all in a single rack, each getting sort of 6 experts, so lots of GPUs, lots of experts happening in parallel. And you're getting 1,800 gigabytes of NVLink connectivity between them, so those tokens can fly across the whole thing. You're not waiting for the communication. You can see right there an 18x speed up in the communication makes communication not the bottleneck. We want to keep the bottleneck on compute. The other challenge with inference, especially for these giant models, is we now have 72 GPUs trying to compute on one model. Super hard, really hard. Like, they're not just sitting in one box or one even OS instances. Every tray is a separate operating system. They're all trying to offload the data, and they're all trying to manage the KV cache. The KV cache is like the working memory of the AI model. When you're using ChatGPT and you ask the next question, it remembers everything before. That's called the KV cache. And when you ask it a question, OpenAI has to go find a server to answer that question, but it also has to get the data necessary, the context data, the memory, next to that GPU. And not just that GPU, but all 72 GPUs in a rack. So when you're talking to ChatGPT, and you are talking to a GB200 NVL72, the rack you showed on stage, it has to do all that routing. That was the genesis for the Dynamo project, which we launched last year. Its idea was to basically do this disaggregation, be able to run pre-fill of the input processing tokens and the decode of the output tokens, and manage all the KV cache across all the data center to move things around. So first thing it does is it does disaggregated serving, so the input processing of their context memory happens on some GPUs. That result goes to the decode GPUs, so we can split those apart and distribute them across the data center, across the rack. We have an enormous amount of KV cache storage, whether you're pulling it from CPU memory or from a local storage or even from a cloud storage. It's designed to be streaming it across the data center. In some cases, it'll actually replicate it. So your your context memory might be stored in a couple different places, so that when a query comes in, Dynamo can say, okay, that GPU is busy, that GPU is busy, but there's another one that has your KV cache, and we should schedule it there, and it fires it off. So that KV routing is critical. As a result, just turning on Dynamo, going from like a naive sort of straightforward approach without any of these things to turning it on once you get it working inside the cloud, 7x improvement. I did nothing. I didn't buy a single new GPU. I just ran Dynamo, and I got a 7x speed up on the GPUs I already have. So this was an idea that had been, a couple people had already been doing it, but this was the first real open source project. And it was a GitHub first project. Every check-in from an NVIDIA developer, you see it in the GitHub repository first. As a result, we have over 217 contributors right now, and over 100 of them right now are external. They're not NVIDIA employees. We get about 90 commits a week. A bunch of major companies are using it right now, from Alibaba to Amazon to PayPal, SoftBank, Meituan. If you order food, you're talking to Dynamo. If you use Pinterest, you're talking to Dynamo, and it's been integrated in all the major CSPs and works with all the major storage platforms for all that KV routing. In fact, there's a talk, I think it already happened, but you should definitely go check it out. This is by engineers at Amazon. So this is Amazon Ads. So Amazon Ads, every time you go to Amazon, you're talking to a GPU with Dynamo, and they talk about how they've improved the efficiency of ad serving, which is a tens of billions of dollars of revenue is actually flowing through Dynamo. So please do check out this recording, and they talk through. We've been working with them for 2 years. They actually use Dynamo with AWS EKS, and they built the system from scratch at scale, and it's working. Okay, so in the end, that's kind of the results you see, and Jensen showed this slide. And it's amazing. Like the compute capability, just the raw flops going from Hopper, the gray, to GB300, the green, it was not anywhere near 50x. But because we've done all these things to optimize communication with the NV switch, with Dynamo, we're getting like a 50x performance per watt improvement. It's just in a fixed data center, you're getting that much uplift. And when you do that, all that performance turns into lower costs. The tokens are naturally cheaper because I can process more tokens per GPU. I can charge less and serve them better, improving my gross margins, or delivering better or cheaper, faster, smarter tokens to user. And this is the Inference Max demo that he showed on stage. I have the belt. There is a belt. What he didn't talk about, though, is that actually, even on the existing platform, it just gets faster. So as we're making more and more improvements, this is actually going from October of 2025 to January 2026. The engineers, I had them document everything they did. And there's about, I think it was over 400 engineers that were optimizing on GB200, the inference stack, running models on that platform. We added a whole bunch of different optimizations. A lot of it's kernel fusions, leveraging NVFP4, optimizing the communication to overlap more with the computation, and also doing more configurable MOE designs in certain input-output token ratios. Overall, it was about 38 different major optimizations. 90+% of them aren't just for DeepSeek, they're for all models. We had to actually simulate about 258,000 different ways of configuring the model and running it on different GPUs. Maybe we should put these experts here and tensor parallel there and pipeline parallel there through simulation. And then we had to test performance. We actually have a whole bunch of GPUs that we rent back from the clouds and ran 1.4 million GPU hours of optimization testing. All of this we did for free. We put it into the software stacks. It went into software like VLM. These are optimizations that went into SGLang. They went into Dynamo, all open source. And for the same data center, same number of GPUs, using free open source software, 4x more tokens. Just straight up 4x more throughput in the same number of GPUs. That's straight bottom line revenue for optimization. It's really hard to do inference. There's so many. I think I've confused you enough. You can feel it. It is a lot of optimizations. The good news is that there are folks like engineers at Nvidia, engineers on SGLang and VLM, all around the ecosystem that are doing these optimizations all the time. So if you get on the platform and you're keeping up with the latest capabilities, you get to enjoy this uplift. And the best part is when a new model comes out, you immediately have the best performance right out of the gate, because chances are they designed and optimized that model already on the day they launched it for this platform. Okay. If you want to learn more about how inference works, there's about over 30 technical blogs published by Nvidia, LMSys, which is where SGLang researchers present their work, or the VLM blogs, which is both VLM community and Meta. There's a nice joint blog with Nvidia and Meta on how some of those optimization works and how they got, in their case, 8x in about 6 months. So do check them out. You can find technical blogs on all these things on the different websites. Okay, coming back to Vera Rubin. Certainly the 10x uplift we're getting from Vera Rubin comes from all the optimizations that have been done across that platform. Faster GPUs, new NVLink, new memory technology, new algorithms, new libraries. And it really nails the sweet spot for AI. On these graphs like this, you have this sort of volume market, which is the sort of interactivity. On the left, we have non-chatbot reasoning, where it's highly interactive, to multimodal, where we're actually going to go ask it to make a picture or make a movie, and I'll show you a demo of that in a sec. To things that are maybe less interactive, but let them think for a while, like coding agents. go program or create this bot or create this application or widget for me, to the deep research side of things, where I'm going to wait a while. In the y-axis, we have just the utilization. We have a nice uplift across the whole board. Some of those things are really amazing, and as they get faster and faster, they actually make the capabilities just more and more interactive in real time. Some of you, I'm sure everyone's asked like Meta or WhatsApp or Sora to make a video. If you go ask Sora to make a video right now, you're talking to a GB200 rack. But Vera Rubin is like a whole nother level of performance where instead of asking it and waiting for it to come back, it can actually be interactive. So one of our partners, Runway, I gave them early access to a rack of Vera Rubin. We do have them up and running in Nvidia. We have actually dozens of racks in Nvidia now with Vera Rubin. PyTorch is up and running. And we gave them a rack and say, hey, what can you do with this? So I'll show you a video right now. Everything you see here was run on a real Vera Rubin with Runway software with help from NVIDIA engineers. And they're going to show you what they're going to do with Rubin. So go ahead and run the video.
AI video generation changes how scenes are created and directed, but can't scale at the speed AI simulation and creator workflows require. Just 3 months ago, Runway's Gen 4.5 generated scenes in minutes. Now their new model, accelerated by Vera Rubin, generates them instantly. That speed changes everything. Instead of waiting for a render, scenes can be directed while they are generated. With just a simple prompt, new frames appear. When new direction is given, the scene updates again in real time. Video generation becomes a live creative loop.
That was not sped up. That was actually real time. The Vera Rubin platform is truly amazing. This is actually a Vera Rubin. Here we have a board with the actual Vera CPU underneath this cooler and the 2 Rubin GPUs here. And you can go see this on the show floor. It's inside of a tray. We put 2 of these per compute tray. The NVLink connectors are right here for the 2 GPUs. And all the other connectivity, the networking and I/O and the storage plane comes in through the back. This singular module is what is powering, 72 of the GPUs, or 36 of these modules, is what is powering this interactive application. Okay. We're of course not done. This is the workhorse of AI, built with parameters and hundreds of billions of parameters, models, processing 8K or 10K or thousands of tokens of context, and producing tokens at the rate of a few hundred tokens per second. But what about what's over there? What's the next click in terms of interactive and agent interactivity? If we can get out here, this is where the future gets really exciting. Here, as we push the AI frontier from 100 billion parameter to 10 billion parameter, a 100x smarter models with contexts that aren't just taking a chat stream, but actually have millions of tokens of context to think about, and to produce it at lightning speeds of not hundreds of tokens per second, but 1,500 tokens per second. We can reach a phase where we can have agents talking to other agents, or AIs talking to other AIs. Remember, they're not gated by how fast a human interact. They can actually interact as fast as they can go. Anthropic did a study about multi-agent systems, and they saw a 15x increase in token generation need, just because the AIs were just talking so fast to each other. And by doing that, by using 10x larger models, you can take things like that, take day-long queries, and do them in just an hour, or a week long, so a lunch break. This interactivity actually is logical. Most of the models today are interacting with a singular model, maybe an ensemble, but it's basically one model that is the smart model. It's like having a smart human. The first AIs were cavemen. Today's AIs are highly intelligent, PhD experts in their field, but they're still one person. Humanity is not the intelligence of any one singular person. Einstein was incredibly smart, but he did not know how to make a cell phone. He didn't know how to make a bridge. He didn't know how to make a skyscraper or Manhattan or run a country. That is because humanity in the information age combines the information of everyone to be able to leverage and think and be smart and to make decisions together. Combining all of the humanity in the information age allows me to enjoy my cell phone, to start a company, to have thousands of employees, and to do amazing things. That's where we're going with multi-agent systems. But to get there, we have to be able to run giant models. They have to interact really fast and also have all the knowledge before them to actually think about and process the large, giant context. That's how we're going to push the Pareto out there. And that's why with the licensing of the Groq IP and what Jensen announced, the LPX, we can push out to that new future. If you think about it, it makes a lot of sense. Today, the GPUs are in the volume AI market, where throughput and efficiency and being able to process tokens economically makes a lot of sense, and it's critical for scale AI. There's this other processor, these ASICs, the LPU, which were designed for extreme low latency. Do one thing, be really, really fast. I might need 1,000 chips, but do that really, really fast and push it out there. But unfortunately, because they're so constrained, they're not very economical, and their scope is actually quite limited. But if we can combine the best of these two things, high throughput and low latency, we can push what Rubin can do out in the Pareto to even faster, larger models. So if you compare a Rubin GPU with a Groq 3 LPU, I have one here. This is a Nvidia Groq 3 LPU chip, an actual one that's being brought up right now and running models right now inside of Nvidia. They're very different architectures. This Rubin GPU, highly programmable, lots of HBM4 memory, gigabytes, 288 gigabytes of memory. Compare it to Groq 3. It only has 500 megabytes of SRAM on the die. The large portion of this chip is just SRAM. That's actually 1/500th of the size. So we don't have a lot of space because we're using it for that fat SRAM memory. But that SRAM is really fast. SRAMs, if you don't know, are using transistors like gates, basically, as memory, as RAM. The most expensive RAM you can do is use transistors for RAM, but they're extremely fast. 150 terabytes a second versus the 22 terabytes a second of talking to HBM memory. That's where if we can combine these two things together, we can actually provide the programmability and the efficiency of the GPU with the speed, the token, bandwidth performance of the LPU. And that's what the engineers at NVIDIA have been doing. We've been fortunate enough to have a significant portion of the Groq team join NVIDIA, combining with our Dynamo team and our disaggregation team to add the LPU to the stack. Here we actually can do prefill on some of the GPUs. That's the input context processing, which happens on GPUs today, like I showed. And then we take that KV cache and we run it on the decode GPUs to generate tokens. We can split the work of the processing of each token. When we need to do the FFN stages, which is the tight matrix multiplies that you often see inside of decoding these experts, we can do that on the LPU racks and do some intermediate tensor state transfer back to the GPUs to do all the complex attention processing that many of the models like DeepSeek or GPT-OSS do. The programmability and the KV cache can stay on the GPU, and only the weights that need to be processed happen on the LPU. And if it doesn't fit on one LPX rack, that's fine. We'll add a second or a third or a fourth. All of that's connected through an optimized Spectrum-X interconnect, where all these racks are cabled up directly and actually going lightning fast between all these racks while overlapping all the communication. There's a huge software effort in this, as well as a system engineering effort to make sure that the tokens are flying. But that's what we built. So the rack, you'll see one at the show floor. Each of those trays has 8 of these chips. They're all directly connected to each other with a chip-to-chip interconnect that then goes to an FPGA that allows them to scale to multiple other nodes and other racks, or connect within the rack using the spine that's behind this rack. We're using the same NVLink spine that we're using for the GPUs We can use those connections, those cable, all the mechanical, all the supply chain, all the connectors, all of our expertise that we did to build the original GB200 rack and the Vera Rubin rack is redeployed in this configuration to connect 256 LPUs together to build a 128 gigabyte SRAM LPU rack. The really most exciting thing about it, and I think didn't get picked up on, is that we're going to deploy this year. So when Vera Rubin comes out in the second half of this year, we're also going to be able to deploy and pulled in the entire Groq 3 capability and technology to deploy this year coincident with Vera Rubin. Now, it's not going to be used for every model. Clearly, Vera Rubin is perfectly fine for the volume market. But for those high-value models that Jensen talked about, we can deploy additional LPX racks to boost Vera Rubin's performance out in the Pareto and do so in an economical way in a token per megawatt that actually enables those next phase of agentic AI models. And this is kind of what it looks like. As you have Blackwell, you have Rubin, and if we add Rubin LPX racks, you can push the Pareto out to serve not a trillion parameter models with million parameter context at 500 tokens per second. In a place where it's efficient, it's actually where Blackwell was exceedingly doing well. Or take it all the way out to 1,000 plus tokens per second, where you have lots of LPX racks connected to an NVL72 rack, and you're still operating in a place where you can deploy those things economically. And because they're so high value, whether it's $150 or more per token, the revenue is materialized because that intelligence is so valuable. Let me talk about one more thing that I'm particularly excited about, and that's CPUs. I've gotten to know our CPU team. I helped launch the original Groq CPU, which connects to our GPUs. And this year, we're actually we're launching a dedicated Vera CPU rack. The reason why people are so excited about CPUs is just the sheer execution and use of CPUs for training and deploying agents. A lot of agents will have a GPU running a model. It'll then tell it to run some code or do a SQL query, where the model or the GPU is actually telling the CPU what to go do to figure something out. You see this all the time. If you ask ChatGPT to write a little program to help you figure something out, it'll actually generate it. It'll go ahead and test the program before giving it back to you. It's doing that on thousands of cores. This is one company that's using 12,000 GPUs to train their next coding model. They then take that model that says, and they give it a test case, right? Solve the Fibonacci series. It gives it to a CPU. The CPU then runs it, and it sees if it got it right or didn't get it right. They actually use 400,000 CPU cores in order to train their model in an iterative loop. The challenge is, of course, if that CPU is slow, everything is going to be difficult. That loop is going to limit you in how fast you can train or how long you're allowed to run that test case to build the next intelligent model. The more faster the CPU, the more time you have to run a test case or a use case, and a more intelligent use case before the result has to come back to the GPU to learn and get better and get smarter. CPUs are starting to get really important for AI. And there's really not a great fit. Like the traditional data center CPUs were designed for dollar per core. These, please, I want cheaper and cheaper dollar per core in the cloud, and don't make my thread performance much worse. They have lots of cores, but they're not very fast as a result. They're optimized for cost, for price. You have gaming PCs, great performance, like run my game really fast. If you have a faster CPU, people hear about it, they want to put that in their PC. They don't have a lot of cores as a result, but they know how to build fast single-thread cores, but they tend to be big, large, and only a few of them, and that doesn't make it very efficient to deploy at scale. And then, of course, you have mobile CPUs, awesome energy and battery life, and these data centers are constrained. We don't have a lot of space, a lot of power. We don't want to waste power, but they're also really slow. So I don't have that. I need kind of all of these things together of plenty of cores, high per core performance, and great energy efficiency. And that's kind of what we have with Vera. Vera actually was designed to be an agentic CPU and is the world's best agentic CPU as a result. It has world-class single-threaded performance. I could go on about all the details. We actually added AI to the front end of this chip. It runs a neural branch predictor. It actually uses AI to predict branches in the code to make better branch predictions, and can do so at 2 branch predictions per cycle natively across a 10-wide instruction set decode. It actually has 3x more memory bandwidth per core than a CPU. We have 88 cores, and each core can get up to 80 gigabytes per core of bandwidth. That's under full load. When all the cores are humming and using the memory system, you can hit some of those numbers. We also added a custom graph data analytics prefetch engine. There's a prefetcher in there that actually is looking for graph and memory hops. We saw this in recommender systems. A lot of recommender systems are designed around graph, and there's actually a custom graph engine in there. And of course, it also supports the full confidential compute support. If you have a model that you've spent billions of dollars of training and you want to deploy it anywhere, you have to encapsulate it into a fully confidential compute enclave. We've run enormous, last checked, I had the team make a bar chart of the performance, 287 benchmarks we've run, everything from SpecInt to Y-Cruncher, which computes digits of pi. This guy can compute 100 million digits of pi in about a second. We've had companies like Starburst or Red Panda, Apache Kafka running 5x faster. Starburst, which does data lake SQL queries, 3x faster. Meta has open sourced a benchmark called DCPerf. That's their backend DCPerf benchmark suite, 2x faster, and obviously an HPC. It's an ideal CPU for the agentic workloads. And we didn't stop there. We just went ahead and put it in a rack. So here's your liquid-cooled CPU rack. It's on the show floor. There's actually 256 liquid-cooled Vera CPUs in there with 22,000 cores. And if you turn on the SMT, you get 45,000 threads, 400 terabytes of memory, and 300 terabytes per second of memory bandwidth. We're using LPDDR5 memory, and that really makes the energy efficiency excellent. And with the ARM pedigree, excellent energy efficiency, 2x perf per watt compared to x86 today, 4x sandboxes, and 6.5x throughput. We did some math, and we actually did some test runs. We believe that this rack can compile the Linux kernel in 1 second. I'm really excited to demonstrate that and show it off, but it has that many cores, that much bandwidth between all the cores. There's actually a fast, full Ethernet spine behind it. We use the spine in the top. There's a Spectrum switch. This thing flies. And we're making it everywhere. We'll ship it as a CPU. We'll ship it as a module. This is the module that goes into that rack. You can see here. It's got 2 Vera CPUs. All of this is your LP memory, power, and then all your IOs of PCIe and other such things. This module is available to system builders for building HPC systems, or we'll just ship the CPU and they can build their own motherboard. Totally fine. One last thing. Power is a big deal. If you start, now that we're building gigawatt scale data, literally gigawatt scale data factories, every last bit of power matters. And it actually presents an opportunity. In a typical data center, you might send in a gigawatt, but you lose a little bit in facility power and cooling inefficiencies. You got to cool these things, but are you cooling the most efficient way? Are you cooling it all the time, or can you moderate the cooling? And then after that, you may have provisioned your data center for the max performance. Well, I know this rack can go up to 100 kilowatts or 200 kilowatts. Therefore, I just take my power and after I take off the facility cooling, I divide by that number. Well, you don't always run every rack at full power all the time at all the racks. And additionally, you might be able to actually modulate the power of every rack down a little bit. Actually, at the high end, the performance doesn't change all that much. You might take power down by 10%, and the performance only drops by 2%. Well, that's 10% more power. I could deploy 10% more racks, or 20% more racks. Or if I look at this whole thing, I could deploy 30% more compute in this wasted envelope if I just had a smarter system and I was intelligent about how much performance I could get out of that 1 megawatt data center. because if I turn it down a little bit, it's a nonlinear curve, and 10%, 20%, 30%, taking it from a max performance state to a max efficiency state can only change performance by less than 5%. But to do that, you got to be smart, and oftentimes and be realistic, and also be aware across the entire data center. So we are building that software. It's called DSX, and definitely check it out. Jensen also talked about scaling up our NVLink. Are we going to scale up in copper? Yes. Are we going to scale up in optical? Yes. This is a picture of polyphony. This is our prototype NVL576 system. What you have here is actually a GB200 system, same as what we see today, except instead of the NV switches not just connecting in copper within the rack, but actually connecting every rack to every other rack using optical. So every one of those yellow fibers and that bundle is connected to every other rack to another set of switches on the side. This builds up a complete NVL 576 GPU scale-up system. The challenge, of course, is a lot of bandwidth. If you didn't think NVLink scale-up was a lot of bandwidth in copper, that's what it looks like in optical. But this is a prototype of what we're going to be bringing up with Vera Rubin Ultra in the next click. We have this actually up and running at Nvidia. We're running workloads across all 500. This is actually a 288 prototype, and be able to actually do training jobs at scale for when we get to the Kyber racks and the Oberon racks when we take it all the way up with Vera Rubin Ultra. Super exciting, and an example of where we're going in the future. There's actually a rack on the show floor, a Kyber of NVL 144. It takes 144 GPUs and puts it in a single rack, which is amazing. It's a collapse of 1, 2, 3. I think half of the system collapses right into a single rack. Okay, I definitely encourage you to check out DSX. This is for at data center scale, whether you want to be using reference design or best practices or methodologies, we make it provided out there. Many of the partners here at GTC are talking about the ways that they're integrating with our APIs for data center management or publishing their own data center management so the AI job scheduler can know whether or not the facility should be provisioning a little extra power. Or vice versa, the grid could be telling the data center, hey, I need that power right now. Can you not provision, take all the 1 gigawatt and can you just run it max at 700 because it's hot outside, we need the air conditioning, and have it back. That's a hard thing, it's a phone call, it's not automatic. We need to turn these things, these gigawatt factories can become power assets to the power companies if we can build those APIs and those interactive things. Right now, those are phone calls. They need to be real-time job schedulers and part of the grid and the infrastructure. That's what DSX actually Flex is an API to interact with the data center. Within the data centers is MaxQ. I'm super excited about Vera Rubin. I definitely have love showing you these things. They're quite heavy, actually. But they are amazing technology, and Nvidia I get to work with all of the teams that build these things, and also more importantly, I get to see what you guys and all the developers here get to do with them. And to take a new thing like Groq 3, IP and team that we only picked up right over Christmas and New Year's, and to not only just tape out and get that chip brought up, but actually to bring that rack to market and to launch it here at GTC. It kind of speaks to the speed at which NVIDIA runs to cover not just the AI market today, but all of the future. So I hope you enjoy it, learn more, ask lots of questions. There's tons of talks. I highly encourage you to go see what other people are doing that can inspire your work. With that, thank you very much. I enjoyed it very much.